Hi, it's Professor Jones. I'm here to work on a couple more problems from section 2.2. Let's take a look at number 30, where we're given the graph of a function and we're asked to use possible symmetry to determine whether this graph is the graph of an even function, an odd function, or a function that is neither even nor odd. So I want to remind you that when you're testing for a function being even or odd, one of the places that you start is replacing x with negative x. So essentially you're trying to find out how f of negative x relates to f of x. If f of negative x equals negative f of x, then f of x is odd. So one of the things I want to do is talk about what does this actually mean graphically. Typically, this is the work you're going to do when the function has been given to you as an equation. But what does this mean when a function's been given to you graphically? So essentially, this means that if f of negative x is f of negative x is negative f of x, then this means that if xy is a point on the graph, so is negative x, negative y. So let's take a look at what that means in terms of the graph that we're considering at this point. So if f is odd, then if 1, 4 is on the graph, so is the point negative 1, negative 4. That's what the previous statement that I've written means for a particular point or particular set of points. So similarly, if 4, 1 is on the graph, then so is the point negative 4, negative 1. So the other thing that we want to look at, so just because that's true for these two pairs of points, it doesn't mean it's true for every point on the graph. So we need something, but it's hinting to us that this is probably an odd function. So we do need just a little something more strongly that we can say that will cover the graph in general. So if a function is odd, then the portion of the graph in quadrant 1 has its mirror image in quadrant 3. If f is odd, then the portion of the graph in quadrant 2 has its mirror image in quadrant 4. So we see there is no no portion of the graph in quadrant 2, which means if this is odd, there wouldn't be any portion of the graph in quadrant 4. We do see this branch of the graph in quadrant 1, and that its mirror image is in quadrant 3. So notice that basically means whatever the coordinates of the points on the graph are in quadrant 1, the mirror image in quadrant 3 will have the coordinates of those points multiplied by negative 1. So the mirror image of point 1, 4 is the point negative 1, negative 4. The mirror image of the point 4, 1 is the point negative 4, negative 1. And so we see that this graph does fulfill that. So it actually turns out that the graph of the function, or the function, is odd, as seen by the symmetry of the graph. So what I'm describing about the mirror images of the graph, so quadrant 1 is mirrored in quadrant 3, quadrant 2 is mirrored in quadrant 4. That's actually the symmetry that an odd function has. So we say that an odd function is symmetrical with respect to the origin. The given function is odd. That's the conclusion that we make on this problem. All right, let's take a look at number 36. Okay, here we have a function, and we're asked various things about the function. The first one being, what is the domain of this function? So notice that the function, if I come in from the left, I see that the function extends indefinitely to the left. So to indicate that in terms of an interval, we're to use interval notation where applicable. So indefinite movement from the left is indicated with a negative infinity. And remember, our infinity symbols, both negative infinity and positive infinity, are always enclosed with a parenthesis when we use interval notation. So notice the graph, every point on the graph has an x value that's smaller than, so notice this point is a point indicating that the function stops, and the x coordinate of that point is 6. And this is actually included in the domain. There is a point on the graph that has an x coordinate of 6. So we notice that all the points on the graph have x coordinates that are 6 or smaller. The range of the function, we notice that the function extends indefinitely downward. So that's indicated with negative infinity. So the y values, there is no smallest y value. Similarly, there is no smallest x value. That's another way to think of what negative infinity tells us in terms of the domain and range. And then notice that the function's y values increase and increase and increase, but the largest y value of any point on the graph is 1. So the domain is all the points that are 1 or the range consists of all the y values that are 1 or smaller. So this includes 1. Now let's talk about the zeros of the function. And another way to discuss the zeros of the function, these are actually the x-intercepts of the. So let's mark these on the graph. So notice an x-intercept touches the x-axis. It's a point of the graph that touches the x-axis. And I'll kind of highlight those points here. Kind of exaggerate them a little bit. So these are my x-intercepts. And I see that x equal to -3 and x equal to 3. So how you answer this if you're doing a MyMathLab problem depends on how the answer is formatted. Sometimes when you're asked for the zeros or the x-intercepts, you're just being asked to give the x-coordinate. Sometimes you're being asked to give the point. To lie on the x-axis, your y has to be 0. So one x-intercept is the point -3, 0. The other one is the point 3, 0. Now when you talk about f of 0, you're being asked about the y-intercept. So f of 0 is actually the y-intercept. So we want the y value where x is 0. So that means if x is 0, the point that has an x coordinate of 0 is going to lie on the y-axis. So a y-intercept is a point on the y-axis. And notice that y-coordinate of that point is 1. So f of 0 is 1. Now we want the intervals on which the function is increasing. So remember, to increase means if you're in an interval of increase, if you're at a point on the graph and you move directly to the right, you're going to have to go up to return to the graph. Another way to think of it as the graph will be rising or be uphill in an interval of increase. So we notice that this extends indefinitely to the left. So that's represented with negative infinity. And this continues until I get to negative 2. So the function increases on the interval whose values, x values, are less than negative 2. Here's how we write it in interval notation. So let's find the intervals of decrease. So I notice when x is 2, the function begins decreasing. And notice to decrease means if you're at a point on the graph and the function is decreasing at that point, then if you move to the right, you're going to have to go down to get back on the graph. So that's what it means that the function is decreasing. And notice how that starts at x equal to 2 and goes on indefinitely. And then we want to find intervals on which f is constant. When the function's constant, it looks like a horizontal line on such an interval. So notice between negative 2 and 2, the function is constant. And as always, when we're giving intervals of increase, intervals of decrease, or intervals where the function is constant, these are always represented with open intervals. Alright, so let's continue with this problem. For which values of x, we want to find the values of x for which f of x is greater than 0. So we want to give the x values of the points that correspond to points that lie above the x-axis. So we see this portion of the graph where my cursor is pointing lies above the x-axis. So let's write that using interval notation. So I see that 3 is on the x-axis, so that means f of 3 and f of negative 3 is 0. So negative 3 and 3 are on the x-axis. So f of 3 and f of negative 3 is 0. And we're being asked for the values where the function is positive. So we see that anything between negative 3 and 3, the function's value is positive. And notice we didn't include negative 3 and 3 because, as we talked about earlier, f of negative 3 is 0, and 0 is not positive, and f of 3 is 0, which again is not positive. So let's find the values for which f of x is negative 2. So f of x is a y value, so we want to go and find negative 2 on the y-axis. and we want to extend ourselves until to the right and to the left until we touch the graph. So we want to find the values of x for which f of x is negative 2. So notice there's two values. One is right at 5. So, for which f of x is negative 2. So we went this way. We went to negative 2 on the y-axis. We moved to the right and the left until we hit the graph, and we see the x that corresponds to the point I hit is 5. And we also see if y is negative 2, we see that x is negative 5. So these values are negative 5 and 5. Is f of 4 positive or negative? Well, let's find f of 4. Here's 4. Now let's move vertically until we hit the graph. And we see that we are lying below the x-axis. So that means that this y value is negative. The graph is below the x-axis when x is 4. Is f even, odd, or neither? So I see that f of x is symmetrical with respect to the y-axis. So f of x is even. A lot of times we just call it f. So whatever's on one side of the y-axis, we have to have the mirror image of that on the other side of the y-axis in order for something to be called even. So it has to have symmetry with respect to the y-axis. And then let's look at this last one. Is f of 2 a relative maximum? And the answer to that is no, because if it were a relative maximum, there would be, even if it was just a tiny neighborhood, there would be a region that we could surround x equal to 2 with, and all y values in that region, corresponding to the points in that region, would be smaller than f of 2. But we see right here, when x is 2, y is 1, and we see that we cannot satisfy the definition of what it means to be a relative minimum, because you can't look at points to the left of x equal 2 and to the right of x equal 2 and find that every y value of each of those points is less than 1, which is the value of f of 2. So we can't satisfy the definition of a relative maximum. So f of 2 is not a relative maximum. We'll stop here.